Okay, so now let's get into what is really going on to give rise to the bonds and molecules. In this lecture, we're going to be introducing hybridization and a model called the localized electron model. Hybridization is something that comes about because in translating atomic orbitals, which I'm going to call AOs, to bonds, we encounter this need to hybridize the atomic orbitals. And I can't really explain this without giving you an example. So I would like us to begin by just considering methane, also known as CH4. So let's think about what we know about methane. We can draw its Lewis structure. So we have carbon bonded to four hydrogens. We know that its geometry is a perfect tetrahedral geometry with 109.5 degree bond angles for all of the hydrogen carbon hydrogen bond angles. So we know what it looks like. We know that it's this perfect tetrahedron. It's going to be a nonpolar molecule. How do its atomic orbitals kind of give rise to it? All right, well, the, let's think back to the chapter where we talked about atomic orbitals. The atomic orbitals in hydrogen are going to be the 2s orbital, which is slightly lower in energy than the 3 2p orbitals. And I'm only considering the valence atomic orbitals here because those are really going to be the only ones that are involved in bonding. In these valence atomic orbitals, I'm going to have the four valence electrons that carbon has. Okay, so these are the valence atomic orbitals of carbon that I just drew here. So let's imagine now what those, or not, let's draw what those valence orbitals look like around carbon. So here's my carbon atom. We know that the 2s orbital is going to be spherical, so I'm going to draw my spherical 2s orbital. And then I'm going to have my three 2p orbitals. So here's, I guess this would be 2py. I can also draw 2px, and remember, they look like dumbbells with opposite shading on their lobes to indicate the fact that I have opposite phase in the wave function in these two lobes. And here's 2pz. Okay, so those are the atomic orbitals of carbon. What about the atomic orbitals of hydrogen? Well, hydrogen just simply has a spherical 1s orbital associated with it. So how can I combine four hydrogens and this carbon with the 2s orbitals and the three 2p orbitals around it to get a tetrahedron? I have the lobes of the 2p orbitals pointing in six different directions here, and then I have this weird 2s orbital. And this arrangement of atomic orbitals simply cannot possibly give a tetrahedral structure. There's no way. So this arrangement of the known atomic orbitals won't give the tetrahedral structure that we know experimentally is the structure of the CH4 molecule. So what we need to have really is four orbitals, four atomic orbitals that are kind of pointing to the corners of a perfect tetrahedron. And we can get that if we take these existing atomic orbitals and do what's called hybridize them. If we hybridize those four atomic orbitals, so basically you take the 1, 2s and the 3, 2p orbitals, imagine sticking them in a blender and then getting out four identical, what I'm going to call sp3 orbitals. sp3 because the s comes from the 1 2s orbital that I've added, and then the 3 comes from the 3 p orbitals, the 3 2p orbitals that I've put in here. If I have four of these hybrid orbitals, they can point to the four corners of a perfect tetrahedron. Okay, another way to imagine that hybridization is to think about taking that 2s orbital and say adding it to a 2p orbital. Okay, so if I do this, and imagine I'm doing it right down the middle here, if I add those two things together, I am going to get a very large constructive interference between the top half, where the in-phase portions add, and then where this out-of-phase portion adds, I'm going to have some cancellation so that I'm going to end up with this kind of shrunken mini lobe on the bottom. So this is going to be what my sp3 hybrid orbital looks like. My sp3 hybrid atomic orbital. So if I imagine carbon with these four sp3 orbitals around it, so I'm drawing these kind of shrunken mini lobes on the other side of it. So this might get actually a little bit confusing. I'm going to erase them. So basically what I'm going to do, just to simplify the drawing, is to erase the small portion, the small bottom portion of the carbon. Now I have four orbitals that are pointing to the corners of something that could be a tetrahedral structure, right? Let me draw that in a slightly neater way. So I'm going to have four hybrid sp3 orbitals. So each of these is one of the four hybrid sp3 orbitals. And just for simplicity, I'm only drawing the larger lobe here. And I'm leaving out the little shrunken lobe that came from the destructive interference. So going back, I had these four valence electrons. So I want to avoid spin pairing if I can. So I'm going to put one valence electron in each of these sp3 orbital hybrids. And now I can imagine hydrogen coming with its 1s orbital and forming a perfect tetrahedral structure where the hydrogen 1s orbital overlaps with one of the sp3 hybrid atomic orbitals on carbon. So this gives four equivalent bonds and a tetrahedral geometry.